So people who have functional ankle instability are by nature unstable. So if you have them balance on one leg, they'll have difficulty doing that more than the average person. And we can measure that using an accelerometer. So an accelerometer is something that measures the acceleration of whatever you put it on in 3 dimensions. And we know that people who have functional ankle instability will exhibit more variability in their acceleration, which we call postural sway. So they will sway more than the average person, which again leads to that instability, which could potentially lead to falls. So that's what we call static stability. And then dynamic stability is stability in performing some kind of task. So like kicking a ball, landing from a jump, something like that. And again, people who have functional ankle instability are less stable when they do that. So, planting your foot to kick a ball, we might have no problem with that, but somebody who has functional ankle instability, again, is unstable and could potentially fall or just not perform the task at the optimal level. So an accelerometer acts very similarly to this pitcher of water, this glass of water. So if I'm holding this glass of water and I accelerate, something like this, the water is going to slosh in the glass. And what happens is if I accelerate this way, then the water is going to want to stay behind because of Newton's first law. And so it's going to slosh backwards, if you will. And so we can tell, if it's sloshing at all, we can tell if it's accelerating. So for example, if I'm not accelerating, if I'm moving it just at a constant velocity, there's no sloshing. Okay. Acceleration is what causes the sloshing. An accelerometer works exactly the same way, except instead of using the gravitational field, which is what is helping to kind of keep this water in its place, it uses an electrical field. So an accelerometer is an electronic device, and so it uses that electrical field, but in a very similar way to what I just showed you. A Fitbit is an accelerometer with just some fancy interpretation software. So a Fitbit measures acceleration like an accelerometer, and then what the software does is it determines what is and is not a step, which is more difficult than it may sound. Accelerometer data is very messy. There's a lot of peaks and valleys. And so the Fitbit has to determine what peak is actually a step and what peak is just kind of noise. So like I said, the acceleration data is very messy. And so the software has to interpret, again, what is and is not a step. That's not necessarily a black and white thing, right? I mean, sometimes it says this is a step when it's not, and sometimes it doesn't say it's a step when it is. There's a lot of research, honestly, going on about the accuracy of these things, and what we're finding is there's a wide variation. So if you take a Fitbit and a Polar Loop and whatever, all these different activity monitors, and you put them, in the same relative place, like you have somebody wear them, on the same wrist, they're all going to have different measures because they all use different software to interpret that data. So it's kind of a question about, what is the true data, what is really going on, how many steps are you really taking, and that's actually a pretty active area of research. Along with that, does more steps necessarily mean that you're exercising harder or exercising more? I mean, I can sit here and just do this, but because I'm seated, it's not really a lot of exercise. So again, there's a lot of research going on about relating those step counts to actual exercise output and seeing if they're more or less the same thing. So we put the accelerometer in a belt, so the accelerometer itself is actually at the small of the person's back. And we do that because that's approximately where the person's center of mass is. And we do that because the center of mass is ultimately what your body is trying to control to maintain stability. The base of support is they name these things for a reason. It's how much base you have to support your body. Again, somebody just standing with their feet shoulder width apart, it's the outline around their feet and the space in between their feet. If the person goes from balancing on 2 feet to balancing on 1, then it's just the outline of their 1 foot that's on the ground. You can change your base of support. If I put my feet wider apart, then my base of support is wider because I have more space in between, my feet. If I'm running, then I have kind of a weird diagonal base of support because again, it's the area between my feet as I'm running. So you can change your base of support as you move, and you do change your base of support as you move. And the center of mass kind of migrates around that base of support, and that's how we determine how stable either you are or you aren't. That's why we put the accelerometer there, because we know that's the main thing your body is trying to control. And from the movement of that center of mass, measured by the accelerometer, we can tell how well your body is able to perform that task. The center of mass, again, over your base of support, we think that people who have functional ankle instability, when they're standing only on that one foot with that quote-unquote bad ankle, that their center of mass is going to vary more. The position of the center of mass is going to vary more. So it's not going to be centered nice and center in the base of support. It's going to migrate around, and it's going to migrate more than the average person. Now, a healthy person, their center of mass still moves around in that base of support, but we think it moves less. Somebody who has functional ankle instability, their center of mass is, again, it's going to vary more in the relative position in its base of support. By looking at the acceleration signal, we can tell if your body is doing basically a good job of controlling the center of mass or not so great of a job. And we do that by looking at how much the acceleration signal is changing. If it's changing a lot, that tells us the person's center of mass is kind of all over the place. And if it's not, it tells us the person is able to maintain stability better. We have the person perform single leg balance, and when they land from their drop landing, they are landing just on one leg. That is a significant challenge to the person's stability, because we're taking their base of support, if somebody's standing on 2 feet, and we're reducing it by more than half, because again, they don't have any space in between. They just have literally the outline of the foot. And so by doing that, we're making it more difficult for them to maintain their balance. And again, that would be true for a healthy person with functional ankle instability. So by challenging their stability more, we're asking the central nervous system to work harder, basically. And so we think that any problems that would come out in somebody's stability who has functional ankle instability, we think we're more likely to see those problems if we put them in those challenging postures.